Alright, so now that we've gone through the system here, I'll flash over to MATLAB and walk you through some of the code and show you what the results can be. Alright, so this is the main script here, and it'll call some other functions, but has some global definitions up here, and then this is N is the number of subcarriers. So I set it at 2048. That's fixed for all simulations here that I've done. You can print out some graphics along the way if you just turn that graphics enabled switch on. That's just for debug purposes typically. And here is the task list. You can set it up for a Rayleigh channel, Rayleigh fading channel, and then just the AWGN channel with different modulation schemes. And that's just to make it easier to set it all up, let it run. You can run through it, get all these results at once, and print it out, and it'll set up the channel for you and everything automatically. Then the reason I did that is it can be some time consuming to actually run the simulation and get some good results, just to get enough error at some of the enough errors at some of the low error points. So otherwise you can get some curves that don't quite look right. They'll have some flare on the ends because you just don't have enough errors. So again, here you're creating this instant SNR is that the magnitude of the channel response. So then this is the function where you look at that instant SNR and you determine the modulation order for each stub carrier that it'll be on. So after you've done that, you can call this function. It creates the modulated data based off the modulation key and the length of the number of subcarriers, and the bit stream that's been created. It takes that bit stream, grabs enough data that it needs to create an OFDM symbol, and it'll modulate it for you. So then you run it through the inverse FFT, and then you can filter it through the previously created channel, whether that's a flat fading, which would be the AWGN channel, or the Rayleigh channel. You add the white Gaussian noise here, perform the ideal equalization, run it through that FFT. Again, some more debug plots if you want. And then here is the adaptive demodulator. So it'll take that modulation key and know which subcarriers it needs to apply which demodulator process to, and then it will it'll actually perform that serial to parallel conversion as well here. So at this point you're all back to the serial conversion, and again, this is that block I was talking about that I'll get to at the end here when I talk about some of the issues that I came across while I was doing the simulation. But this is the synchronization with the preamble, just to see how far. Again, I'll talk about that with it, but it synchronizes up. So then when you run your bit error curves, and you are aligned to the same points, otherwise, again, you can get some large errors which are misleading and can throw the simulation off. And the rest is just keeping track of your bit errors and then your throughput analysis as well. So then the main two plots you're worried about afterwards are your bit error performance, which can be seen here. And this is for the Rayleigh channel, so frequency select fading channel. The gold curve here being your adaptive modulation technique, and then the blue solid line is your theoretical BPSK. So that would be the best in terms of error performance, the best you're going to be able to achieve with the PSK scheme. So you can see the adaptive modulator is right there with it. Again, some of these points might be off a little bit simply because I might not have ran it long enough to get the optimum number of errors. But as you go up, the higher the order of the modulation, it's to be expected, just simply because you have more symbols in the same signal space, so it's going to be harder to make the correct error. So this looks about right. It's what you would hope to see as far as error performance, and the adaptive modulation is right along with the theoretical BPSK curve. And so then the next window you need to run the analysis on is the efficiency of the OFDM system. And so then you're looking at basically how many bits per second per hertz, or how efficient you are with your spectrum. And as you can see, it followed the error performance of BPSK, but BPSK asymptotically approaches the 1 bit per symbol, because that's all that modulation scheme has. That's the limit of the modulation scheme. But the adaptive modulation scheme throws this curve here, which shows that as you increase your SNR, you increase your throughput performance too, which, if you're not going to have errors in some of these other modulation schemes, you should utilize that spectrum to the best of its ability, which the adaptive modulation scheme shows here you do. So I'll quantify some of these results in this next slide, but those are the curves that are those are the results that you get out of this simulation. So we can go back here. Alright, so now that we're done with the system overview, I will go further into the simulation results of what we actually achieved. So again, as you can see, this is the AWGN channel. So this is a flat frequency select fading channel. So again, you'd like to see this line up with the BPSK in terms of error performance. That means you're optimized for your error performance. You are achieving the best possible error performance you can, which you can see the gold here lines up there. So that looks good. And the throughput analysis here, it might look a little funny right away, but it's easily explainable when you think of the AWGN channel as a flat channel. So we looked at those tables. The table that I explained was used to create that modulation key. The plateaus here are when the channel falls within that range, it will have a plateau, and then as that channel changes, it will go up in spectral efficiency, then it'll plateau again when the entire channel is within a certain range, and it's one and only one of the modulation orders. That's where that plateau is. So again, the AWGN channel is it's more to double check the simulation, make sure that you're getting the results you would think, and make sure that you're not having any real systematic problems within the simulation. So after this, I moved on to implementing the frequency select fading channel. And again, these are the results that were viewed earlier. So as you can see, in terms of error performance over a QPSK, I typically look at the 1e to the 3 point. You can see for the adaptive OFDM, it's right about 24, 23, and then the QPSK is this green. It's about 36, so it's 12 dB gain that you get between the adaptive modulation and the QPSK modulation. And then if you want to look at that in terms of throughput gain, you can look at the 1e to the minus 3 point for the for QPSK was at, again, 36, and that would mean that the QPSK had about 2 bits per second per hertz throughput, where the adaptive modulation scheme, it's a little hard to see here with the shrunk down plot, but if you could move this key out of the way, you could see that it's actually about a 2x gain. The adaptive modulation is approaching 4, so you're getting double the throughput and an increase in error performance. So there's really no reason to do it aside from the complexity. You have to think about the complexity as well, but in terms of error performance, the adaptive modulation scheme really presents a lot of gains that are possible. So again, I keep talking about this preamble and synchronization that was causing problems that needed to be added. So as you can see in the OFDM symbol, you have these subcarriers, and it's created with this data stream. And what was causing problems with the frequency select fading channel specifically was once you filter it, you get this time and phase offset, and depending on how much phase and time offset that introduces into your OFDM symbol, you could be off by a complete symbol, and that means that when you go and detect the number of symbols that you have, if you've been shifted off by more than one symbol, your whole data stream is shifted off. So you don't actually, you think you're on symbol 0, really you're detecting symbol 1, and that will, when you run your error analysis, that obviously causes huge problems in that 1 bit shift that occurs. So one way I combated that was basically you create this blue chunk of data, which is referred to as a preamble pattern. It's just a repeated known pattern that the receiver synchronizes on, and then it just skips ahead each known fixed pattern length, and it looks for this start of message sequence, and it's just a unique 1-bit sequence, or I use a 12-bit sequence, but you can use however long you want. And once you're synchronized onto the preamble pattern, it just keeps looking for this start of message, knowing that after that start of message, your data payload comes, and that's really where you want to do your error analysis. And so again, this will take away from your throughput analysis or throughput efficiency, but it's necessary in order to actually perform any sort of error analysis on the system. So another simulation challenge was the partial symbol reception and trying to determine where the subcarriers are if you only had a partial data block that was resolved. But yeah, again, that was a minor problem compared with the synchronization of the receiver and the transmitter with the phase and time offset of the channel. Okay, so this simulation obviously, it assumed a lot of things. It assumed that you had this information available to the transmitter and receiver at the same time and the same information. So that's one area for future work, is the implementation of this back channel for full duplex, so the receiver and transmitter are actually communicating again through the same kind of channel. So if the receiver detects something and has to communicate with the transmitter, if there's errors in that communication, what will that do to the system? Again, there's the ideal equalization was performed when you're estimating the channel. Different types of equalizer techniques can be used, but if errors are made there, what kind of impact will that have on your throughput or your bit error curves? So non-ideal channel estimation, that's more future work that can be added to the simulation. Obviously, a simple change would be the change of the modulation scheme to see what QAM and PAM, or pulse amplitude modulation, what would those do? How would those perform in the same setting? And then the adaptive algorithm, as I stated in the beginning, this was strictly to look at error performance, and then along with error performance, you also typically look at the throughput analysis too. And but we were optimized for the error performance, trying to get the best bit error rate possible. But you can look at the power limitations of a transmitter to try and optimize for power limitations, try and optimize for spectral efficiency if you are limited to the amount of spectrum that you have. And then a combination of all of those. If you want to optimize for one based off certain conditions, if you want to optimize for all of them based off of a certain set of parameters, you can really try any of those, and changing the tables, changing those thresholds. Those are all more additional work that could be done and tested out with this. So there's a lot of future work that could be implemented in with this, and some, I think, interesting research opportunities also for this project. So in conclusion, there's a 10 to 12 dB error performance over a QPSK system for the 1e⁻³ bit error performance, and then a 2x gain if you look at where the 1e⁻³ point is on the QPSK, and a 2x gain with throughput performance, that is, if you look at the 1e⁻³ points between the adaptive and QPSK OFDM system. So once again, the adaptive modulation algorithm works, and that is the most important part of this simulation, is to show that there is some validity to the idea of trying to optimize where you send information and when you send that information in the certain subcarriers of an OFDM system. So these are my sources. Thank you. If you have any questions, please feel free to respond to the video or email me. Thanks.